In this video, I want to talk about scalar methods versus vector methods, and you may find one of these concepts easier to use given the particular situation. But there are two scalar methods which we've talked about briefly so far, and the first one is using the principle of transmissibility. For example, if we have a bar attached to a wall with a force applied at an angle like this, we can try to find the perpendicular distance to that force by drawing an extended line of action and try to find that distance that is perpendicular to the line of action of the force. Or we can use Varignon. Varignon allows us to break the force up into its components and then find the moment of each of those components independently and then add them together. So the first is using transmissibility, the second is using Varignon. And let's apply that to this example problem right here. We have a force applied to a bar. It's in a curved shape, and let's use Varignon by breaking the force up into its components. So I'll say that there's going to be a component going this way and a component going this way. I have an angle of 45 degrees, and so that means this is 45 degrees. So I'll call this 500 cos 45, and this one would be 500 sine 45. Now, what are the distances that we care about? Well, for this component, I am looking for this distance right here. So let's write that distance there, which will be 3 meters plus this distance. This is the radius is 3, so this distance here would be 3 cosine 45. So this is distance 3 plus 3 cos 45. This distance here, right here, for this lever arm, the lever arm for this force here would be that distance. And that's going to be 3 times the sine of 45. So then let's just add them together. I want to find the total moment about O, where this is going to be positive. So I'll say that that is going to be 500 sine 45 times its lever arm of 3 plus 3 cos 45. That's going to be this force times that distance. Now this force here is tending to rotate it going in this direction. This force, or this component, is tending to rotate in the positive direction, but this one is trying to rotate it in that direction. So this component will be a negative. So this will be negative 500 cos 45 times 3 sine 45. You add those together and you get this value of 1060 Newton meters. Okay, that's using Varignon to break it up. Let's use transmissibility and see if we can come up with the same answer. For example, if I looked at the line of action of the force, the line of action of the force is right here. I can basically use transmissibility to extend that force down to here, and now this will be the lever arm. So the lever arm here is just going to be 3, and the force here is going to be 500, like that. So all we're looking for then is the moment about point O is going to be 500. Now we can use Varignon again. We can say that there's going to be a component this way and a component this way. So this would be the 500 sine 45 component, and the lever arm is just going to be that 3. So the same rule applies. 500 sine 45 times 3. The cosine component has got the line of action of the cosine component going through point O, so there's no lever arm. You add those together and you get 1060. So you get the same answer, which is always what you're looking for, depending on whatever process you're using. Now those are the scalar methods. What I want to do here is talk about a vector method using the cross product. You may be familiar with cross product from prior work in physics or calculus, but we're going to apply it here and try to see if we can come up with the same answer using the vector method. Okay, so the way we look at cross products is we're saying that we're going to use a 3 where we're going to use a matrix and do a determinant action, calculate the determinant of a matrix in order to find out what the moment about point O is. First of all, we have to find out what the force is, and the force will have some point here. And the way we're going to do that is we're going to do the cross product of that force, that Cartesian description of the force, cross it with any point on the the r, the radius, or the r vector can be from the point that we care about to any point along the line of action of the force. In other words, the r vector could be anything. It could be this one right here, or it could be any point along the line of action of the force, and they all work. They all calculate out to be the same. And we're going to use this cross product method where we're going to say that we're going to put the I in the j here. The moment about point O is r cross f, and we're going to put the r vectors in the first row and the force vectors in the second row. Again, both r and f have to be in Cartesian description. And the way we do that is we're going to say that times that minus that times that, and that gives us our calculation. We'll get to 3D in the next video, but for right now in 2 dimensions it'll be very simple: rx times fy minus ry times fx. Alright, so let's use that concept to come up with a vector description of some r vectors. And again, the r vector can be any point, or can be to any point along the line of action of the force. So here's the line of action of the force. First of all, let's find out the vector description of our force. So we have a cosine 45, so I think we can just say that f is going to be equal to 500 cos 45i plus 500 sine 45j. Now the r vector, again, can be from the point that we care about to any point along the line of action. So first of all, let's just call that our r vector. So let's just go ahead and define that. That's a good one. It is certainly going to the line of action of the force, so that is r. So let's define r. In this case, we know that r is just the, and this is a position vector, so it has magnitude in length, and that's what we're looking for. It's not the unit vector, it's a position vector. So it has this much in the x direction and that much in the y direction, and I think we've pretty much calculated that already. So I'm going to put r is equal to 3 plus 3 cos 45 I plus 3 sine 45 j. Alright, let's put those into calculation, into our little matrix, and see if we can calculate the moment using cross product. So the moment about O, and in this case we're going to do a vector description rather than a scalar description of the force. So that's going to be equal to r cross f. So let's build our matrix I and j, and what we're going to do is put the r vector in the front row, or in the top row. If I calculate that out, I got this is equal to 5.121, and this would be 2.121. Then the f vector going below is 353 and 353. In other words, calculating the values of each of these and put those in there. Alright, let's do our calculation. What we say is that we're going to multiply that times that minus that times that. So let's do that. We got 5.121 times 353 minus 2.121 times 353, and you get 10,000 or 1,060 Newton meters. So you get the same thing that we did using the scalar approach, or the scalar method. Alright, then there's another way that we can look at this by using some of the transmissibility understanding, and that is that we don't care where along the line of action we draw this, or we do this calculation. In other words, there's a variety of r vectors that might work. So let's look at this one. Let's say that we did, instead of the r vector going from here to here, let's say we did an r vector going from here to here. In other words, we know that the line of action of this force goes along there. Well, that's where the line of action is, so this would be a perfectly good r vector. So let's call that r2, and you can see that that is only going to be 3 in the I direction, and that's what I've shown here. The force vector is going to be the same, so using the cross product calculation, we do the same thing. 3 times 3 and 0, that's going to be our r vector, 353 and 353, and you can see that when we calculate it out, we get the same answer, which is good.